Okay, so I am doing my video on kinetics, specifically the collision theory, mechanisms, and catalysts. First of all, kinetics is a study of rates of chemical processes. There are many things that can increase or decrease the rate of reaction, but the idea surrounding how a reaction occurs in the first place is called the collision theory. This theory is based upon the fact that the reaction rate equals the frequency of effective collisions. For a collision to be effective, it first has to have two things. The first thing is that it has to have enough energy to overcome the activation energy. E sub A is the amount of energy that it takes for the reaction to occur. If the molecules do not collide with enough energy, then the reaction will not happen. The second thing is that the two molecules must collide with correct orientation or geometry. This means that, for example, the nitrogen of one molecule must collide with the oxygen of another molecule in order for the reaction to occur. This translates to the transition state theory, which states that the geometry of the molecules undergo changes at a place called the transition state. The transition state is a hypothetical place. Scientists don't actually know what happens because the molecules break apart and form products so fast. Next are mechanisms. A mechanism is the sequence of steps that lead to a chemical reaction. An elementary step is each individual step within the mechanism. A reaction may have a lot of elementary steps, or it may only have 2 or 3. An intermediate is a chemical species that is part of a mechanism but does not appear in the BCE. You can see intermediates when the mechanism is written out. They are formed as products in one step but then consumed as a reactant in another step, so they are not a final product. And a catalyst appears as a reactant and a product, meaning that it is not consumed. In a reaction mechanism, you'll see it at the very beginning and at the very end. Sometimes it isn't even written in the equation, but over the yield arrow because it can be a solid catalyst. I'll go further in depth on catalysts later. But here's an example of a mechanism. It has 2 elementary steps and a final BCE of 2NO plus Br2 yields 2NOBr. To get the final BCE, all you have to do is add the 2 elementary steps and cancel out the same ones on both sides. The rate determining step is the step that literally determines the rate. It's the slowest step in the reaction, which means that the whole reaction must match its speed. You can use the rate determining step to find the orders of the reactants in the rate law. The molecularity of the reactants in the rate determining step matches the orders. This basically means that the coefficients of the reactants match the exponents in the rate law. Here's a chart that explains that. All of these steps are the rate determining steps. You can see that in this step, 2 A's and 1 B are reacting. You can take the coefficients of each and make them the orders in the rate law. So the rate law then becomes K times concentration A squared times concentration B. This type of reaction is called termolecular because 3 molecules are reacting. Bimolecular means 2 are reacting, and unimolecular means 1 is reacting. Now here's catalysis. Catalysis is the increase in the rate of a chemical reaction of 2 or more reactants due to the participation of an additional substance called a catalyst. It is important to know that the catalyst is not consumed in a reaction. You can see that in a mechanism. A catalyst provides an alternate pathway for the reaction to occur. This pathway has a lower activation energy than the original pathway. This basically means that the molecules can collide with less energy in order to form products. Since there is a higher frequency of effective collisions, the rate of reaction increases. A catalyst is usually in the rate determining step because it is the slowest step. Some examples of catalysts are enzymes, which are in your body, a nickel surface, and vanadium oxides. Okay, so this graph represents the idea behind an increase in temperature. The temperature increases the average kinetic energy of the molecules. If there's more energy, then there are more collisions meeting the activation energy, which is shown right here. And since there are more effective collisions, the rate of reaction increases. This graph shows a 2-step mechanism. The activation energy for the first step is right here, And the activation energy for the second step is right here. You can see that the first step has a higher activation energy than the second one. This means that it is the slow step and the rate determining step. The transition states are labeled, and that is where the reactants break apart and form products. This third graph also represents a reaction mechanism, but this one has 3 steps. You can see the breaking of bonds and formation of bonds right here at the transition states. And you can also see the activation energy right here. And here, and this little one right here. The first step has the highest activation energy, so it is the rate determining step. Since the molecularity of the rate determining step matches the orders of the reactants in the rate law, you can say that that rate equals K times concentration NaCl squared because of the 2 coefficient right here. This last graph shows how a catalyst works. The black curve is the original pathway, and the red curve is the catalyzed pathway. You can see that the catalyzed pathway has a lower activation energy than the original pathway. But delta G is still the same because it is a state function, meaning that it is independent of the pathway. Okay, so now here's the FRQ. It says, consider the following general equation for a chemical reaction. A plus B yields C plus D. And delta H reaction is negative 10 kilojoules, so it is exothermic. Part A says, describe the 2 factors that determine whether a collision between molecules of A and B result in a reaction. So this relates back to the collision theory. So A and B will react if they collide with enough energy to overcome the activation energy, and if they collide with the correct orientation or geometry. They must collide in an orientation that will allow the bonds of each molecule to break and rearrange themselves in the transition state to form products. Part B says, how would a decrease in temperature affect the rate of the reaction shown above? Explain your answer. So, a decrease in temperature will cause the forward reaction to decrease. Kinetic energy is directly related to temperature by the equation Ke equals 3/2 kT. If temperature is decreased, then average kinetic energy of the molecules also decreases. If the energy of the molecules decreases, then some of the molecules will not have enough energy to reach the activation energy, and there are fewer effective collisions, which means that the rate of the forward reaction decreases. Part C says, write the rate law expression that would result if the reaction preceded by the mechanism below. So you can see that the second one that says AB plus B yields C plus D is the slow step. But since the fast step above it is in equilibrium and it's A plus B equilibrates to AB, you can substitute AB with A plus B. So the slow and rate determining step becomes A plus 2B yields C plus D. And since the molecularity of the rate determining steps matches the orders of the reactants in the rate law, you can say that rate equals K times concentration A raised to the first power because A has a coefficient of 1, and then concentration B squared because B has a coefficient of 2. And part D says, explain why a catalyst increases the rate of reaction but does not change the value of the equilibrium constant for that reaction. The catalyst increases the rate of reaction by providing an alternate pathway for the reactants to react. This alternate pathway has a lower activation energy, therefore, there are more collisions, meaning the activation energy and more molecules reacting to form products. The value of the equilibrium constant does not change because the concentrations of the products and reactants are still the same.